All right, hello everyone. My name is Ariel Rokem. I'll introduce myself in just a second here. You are here for the April CloudBank Cloud Clinic, and today's topic is the sustainability lens on cloud computing. So we'll talk about sustainable computing. Let me start presenting my slides here. Um, do you see my slides in present mode? Yeah, okay, good. Okay, so first I'll just start with myself. I am a research faculty member at the University of Washington, but I will actually be soon moving, and we're talking less than a month, to the Center for Addiction and Mental Health at the University of Toronto. So if you want to look for me, that'll be the place to find me starting mid-May. In my own work, I develop artificial intelligence, machine learning, data science methods for analysis of neuroscience data. So my specific sort of domain interests are neuroscience. And I use these tools together with large open data sets to study a range of different questions, like how do baby brains develop early in life? Or what is the relationship between retinal disease and brain aging? What parts of the brain mediate the relationship between school quality and learning to read? And how did the COVID-19 pandemic affect the development of brains of adolescents, young people? And so on and so forth. And you can learn more about me at this website, which is my personal website. I should mention that I've been using cloud computing in my research for over a decade, so I'm really interested in cloud computing as a tool, and it has a lot of advantages. And if you're here, you're sort of interested in these advantages. But something you might not be thinking about necessarily is the impact that use of cloud computing has on sustainability. What's just the story there? So, just to give a little broader context, this is from a UN report. Environmental impacts of pretty much everything we do are important because we are on track to a global warming of 2.7 degrees Celsius by the end of the century. Again, I'm a neuroscientist, not an environmental scientist, so I don't actually know much about this, except that I do understand that the science is pretty conclusive that this trajectory has pretty catastrophic implications for all of us. Okay, back to computing, where I feel more comfortable. Computing has many environmental impacts. The extraction of materials to build computers has environmental impacts. The waste products of old computers have environmental impacts. And for large-scale computing facilities, such as the ones used to do cloud computing, there's issues of noise, there's issues of land and water use that are affecting the environment. So there's a range of different ways in which computing affects the environment. And today I will only discuss the issue of energy consumption and how we can sort of think about energy consumption more effectively when we do cloud computing. So broadly, and this is really old, this is from 2018, so it's probably not up to date. But in 2018 already, the forecasts for energy use of various kind of categories around computing was for this kind of very steep increase, with some of this associated with just the internet broadly, and data storage, just the fact that we're storing more and more data. So that's here on the right, and internet traffic. To be completely honest, we as scientific, as researchers, not scientific, but researchers, general research computing probably doesn't take a lot of this, but we definitely contribute in this. Moreover, overall, computing counts for about 4% of human-made greenhouse gas emissions, which is much less than, say, heavy industry, which contributes about 24%. But more than things like aviation or shipping, so it's not an insignificant amount. And if we can do something to improve our footprint in that respect, maybe we should think about that. And so I'll talk today about some of the things that we can do. One thing that we can do is shift our use of energy to procure renewable energy. We'll talk about how you can do that with the cloud in just a second here. The other thing is to make our own compute more energy efficient. And then the last thing is to change or maybe shift our conceptual frameworks about things that we're doing in line with a more sustainable approach to computing. So I'll talk about all three of these things, and I'll actually start with energy efficiency. So the first thing that I will point out, and may or may not be obvious to folks who are here in this telecom, is that the cloud can be a very energy efficient computing resource compared to the alternatives. So this is from a study conducted by the National Resources Defense Council together with a consulting firm called WSP. You can find it in this link, and we'll share out the slides later, so you have these links. And what their analysis is about more standard, maybe less computing, like scientific computing kind of workflows, but in this case, deployment scenario of office productivity applications. So each one of these deployment strategies here on the x-axis, on-prem with no virtualization, co-location with no virtualization, on-prem with virtualization, private cloud or public cloud, all of these different settings have a really large range actually from best practices to worst case in terms of their carbon emissions per user. And so you can think about like using the best practices would be, for example, updating hardware as needed and use of more renewable energy resources. What I'd like to point out is that all of these kind of ranges are affected by things like how much compute are you packing into your existing instruments. So instruments that are plugged in and are just sitting there idle do use energy, even though no computing is taking place on them. And if you think about like different users, for example, in an office having different computers, each one using maybe a small portion of the available memory, available CPU on their computer, that is a much less efficient use of energy than if you have one big computer that they all connect to. So that's the difference between on-prem with no virtualization and on-prem with virtualization. Well, virtualization in this case means packing multiple users onto the same machine and might be the model that you use if you're using, for example, high-performance computing, on-prem high-performance computing instrument in your institution, or maybe something like one of the large national facilities for computing. What I would like to point out is that just thanks to the scale, the kind of economies of scale and their ability to really pack in a lot of compute and maximize utilization, the public cloud is here. And public cloud here is meant commercial cloud vendors like Amazon Web Services, Azure, Google Cloud, those kinds of things do reach under best practice, reach the best carbon emission per user. So that's just, if you needed another reason to use the cloud, and you're maybe cloud curious and need yet another reason, that is, in my opinion, a compelling reason to go to the public cloud. Here in this case, private clouds means something like some of the other programs that are administered by the Access, the SF Access program has other kinds of programs that are more like what you might call a private cloud, but also something that maybe a company might install, where they have like large data centers that are available to many of their users. So it might not be as applicable to many of us academic researchers. Let me pause here for a second and see what questions people have so far. Okay. If no questions, I will then go on to my next slide. And just to point out that in terms of efficient energy use, the cloud within the cloud vendors, the commercial cloud vendors themselves, you have tools that can help you be more sustainable. Different vendors have things like this AWS Sustainability Console that lets you monitor your energy use and the efficiency. And I'll show something from that later. You can also do things like simple comparisons to see how efficient you are in terms of your utilization of carbon-free energy. So here, I've picked out these two Google Cloud regions just to point out to you that if you use US East 1, which is probably for most users in the US, if you start a Google Cloud platform compute console and you ask for a machine, the default is probably going to be US East 1. It's, I think, one of their largest regions. And that one has one of the worst carbon-free energy percentages and one of the highest grid carbon intensities. possible within any of the regions. If you just move your compute to Europe North 2, which is based in Stockholm, Sweden generates their carbon-free energy is 100% with grid carbon intensity that is, orders of magnitude smaller. So if you don't care where your compute is happening and you want to use less carbon intense energy, do your compute in Stockholm instead of doing it in South Carolina. Okay. And so there are different ways of assessing the impacts of it gets really, really complicated. And if you go to any of these cloud vendors, many commercial users of the cloud platforms have sustainability concerns that are related to compliance or to goals that different companies have. So they have a lot of tools around that. And if you go, it gets really kind of confusing. I'll just point out two distinctions or two distinct different ways that people relate to these measurements or assessments of the intensity of the compute in terms of its carbon emissions. One was called market-based measurement, MBM, and that's really complicated. And that's because you can do a variety of different kinds of accounting in order to measure your carbon efficiency. For example, you can say, well, I'm using a lot of carbon up over here, but I'm also buying some carbon credits. Every time I use over here, I have committed to buy some carbon credits over here or plant some trees or save somewhere else. So I can say that this is less carbon intense than over here. And that gets really complicated, although you can get an estimate from the cloud vendors for your carbon budget based on that. Another much simpler approach is this location-based approach, LBN. And that's along the lines of this down here. AWS actually recommend using this app, electricitymaps.com, that can tell you about the energy intensity of electricity usage in different geographic locations. So here we are in Virginia, for example. I've clicked on Virginia, which is where AWS's US East 1, their kind of default region lies, and you can see that it's 40% carbon free and very little renewables. But again, if you go to Sweden, it's 100% carbon free and 100% renewables because they do a lot of hydropower. So again, if all else being equal, if you don't care where your simulations are running, where your data sits, put it in Sweden rather than putting it in Virginia. That's location-based optimization. And then again, the cloud computing vendors, AWS actually, in my opinion, leads on this so far. They will give you pretty detailed monitoring tools to see the impacts. So here we are actually in this MBM emissions. So this is market-based. This is based on a bunch of accounting. This is a project that I ran this last year through CloudBank, actually, and the National AI Resource. I forgot what the second R stands for. The pilot project of the NAIR. We ran this on AWS. We trained a big model. So you can see we're using quite a bit of emissions, 0.461 metric tons of CO2 emissions. For comparison, one person's Seattle-Toronto flight impact is about 0.56 metric tons. So our project is actually pretty substantial in terms of its impacts. But they also estimate the emission savings, and the emission savings in this case come, I think, from using location-based. We just put this in a location. In our case, actually, we used US West 2 in Oregon, which also uses hydropower. So if for some reason, for some compliance reason, your data needs to reside in the US, US West 2 is better than US East 1 in terms of its carbon. And then again, the AWS lets you monitor your emissions by service, your emissions by AWS region, and so on. Which brings me to the next topic, which is, there's something in the chat. Let me just look at the chat. Yes. National AI Research Resource. Got it. Yes. Okay. So the next thing I want to talk about is like if you want to get really granular about this and optimize what you do, there are tools available that will let you estimate the carbon emissions of your code. So this is a little distinct from the cloud stuff that I've showed you so far, but I think could also be interesting for you all. I just want to point out a tool that will let you estimate the CO2 emissions of your code, which is Code Carbon. It's a Python library that instruments your code to estimate its energy consumption. Um, I'm not, I'm not, I don't know all of the details of their modeling, but they do take into account things like whether you're using a cloud computing or on-prem and what operating system you're running with and whether you have a CPU, GPU, and so on. I thought I'd show a little demo of how this works. So I wrote some, based on their examples, I wrote a little bit of these kind of Jupyter notebooks that show this so that you can see what this looks and feels like. So I've installing Code Carbon as a Python library is relatively straightforward. Just making sure, can you see my VS Code window now? Yes, okay, good. Um, and what they've implemented is this thing they call an emissions tracker. So here I'm importing that from Code Carbon after having installed the library. And that this emissions tracker class can create an object called a tracker, and you can start that tracker and it gives you some information about what it's doing. You can run multiple at the same time, and it's having some issues on my machine, but it will still save emissions data into a file, a CSV file here. For example, if I do some compute, I can get, and then I stop the tracker, I can get an output here that will tell me how much, in this case, kilogram of CO2 was emitted thanks to this compute. Fortunately, just for this demo, it's not a lot of CO2 that was emitted. And it will also, like I said, save a file. Here I've read this file using pandas, and it tells me about my emissions rate. The emissions, very small in this case, how long that took. In this case, it took long, and that's just because it took me a while between executing this and executing the stopping. So it times between tracker start and tracker stop. And this is in seconds, I believe. And it stores that, and you can do different experiments also in order to compare different computing modes. So one way for you to improve your carbon footprint is to think about what you're doing when you're doing computations. I'll show you an example of that with a little bit more detail about Code Carbon here. In addition to the emissions tracker that I showed you before, Code Carbon also implements a function decorator that allows you then to decorate your functions so that you can, at the level of a function, individual function, estimate carbon footprint. In this case, I am going to show you an example based on their examples of computation of the Fibonacci series. The Fibonacci series, probably known to many of you, is the series such that every item in the series is the sum of the preceding two items. And there are many ways to compute the Fibonacci series. There are different algorithms you can use. In this case, I'm asking different functions to compute up to the target number 40. So here's the first approach to this. In this case, I'm using the start and stop tracking approach that I've shown you before. I've implemented a recursive approach to computing the Fibonacci series, and I'm going to estimate the carbon footprint of that. It's going ahead and computing that. That takes a little while here. And I should say also, it does along the way provide also the energy consumption in your window as well. Here's another way to compute this. Is this Binet's formula for computing the Fibonacci series. Turns out there's a closed form solution for this based on the relationship between the Fibonacci series and the golden ratio. So I'm going to compute that here. In this case, I'm using a context manager, a Python context manager. So in this case, I'm starting one of these objects as tracker, and then computing and everything that is within this context will be tracked. So that's happening here. This takes much less time because it's a closed form solution. Finally, there is a another algorithm here. And in this case, I'm using the Python function decorator, track emissions. Again, I'm giving it a project name so um, that I can distinguish between my different algorithms in the end. I'll show you that in just a second here. Here I'm running the decorated function. So this is the most straightforward. Whenever I run this function, it gets tracked. In this case, it's this backwards approach for computing the Fibonacci series. And that ran too, and it's done. And so now I can compare the different things by the different approaches by reading my stored CSV file. I have my first tracking is still stored here. This is the thing that I did in the other notebook, but now I have my different project names, recursive, golden, and back, and I can look at the duration of these and the emissions footprint. You can see that the recursive algorithm is just orders of magnitude more carbon expensive than these two other approaches. The closed form solution being the most energy efficient, of course, because it really happens immediately, basically. So that's just to give you a sense that if you're doing something and you're going to do it a million times or a billion times, and each time it uses a little bit of carbon, and you're worried that well, not worried, but your concern is minimizing that impact. Benchmark it, use something like Code Carbon. Like I said, it will record, for example, whether you're using it on a cloud or not. So you can make measurements or estimates, I should say. These are not actual measurements because it's not directly measuring the energy. It's estimating it based on a model. It will give you a comparison for doing this on, I don't know, my laptop versus on the cloud, and you can see how much your utilization improves doing that. Okay, what questions do people have about Code Carbon?
Can I ask a question?
Yes, please.
So, Code Carbon and tools like these, I think you just ran them. They seem to be quite easy to work with. But
Yeah,
when you're talking about the cloud, you could have different users running different processes on the same physical machine.
that's right.
We've been doing some research here trying to see how easy it is to get estimates in a shared environment like this. Do you have any comments on that? Again, the example you showed is great, but this is on one machine. But if you're looking at CloudBank, let's say, you have users running VMs from all around the world on one
Yeah.
physical machine located somewhere. How well do you think these techniques work, or is there any comment on that?
Yeah, I will say again, this is an estimate. I actually, while preparing for this, I was looking around for somebody who would, if there's any validation, and there was one paper I found that had pretty grim validation numbers for this. So I'd say it should be taken with multiple grains of salt. Yeah,
I
I'll
see.
totally.
Any chance you remember what that paper was? I'm very curious.
No, sorry, I don't remember. Maybe I should have pasted it in here as well. Somebody who did like direct measurements of energy consumption on their
Okay,
actual
and I guess you're saying the finding was that these estimates could be quite off.
yeah,
Is that okay?
yes, could
All
be
right,
off
thank
by
you.
like double digit percentages. Um, yeah, which is unfortunate. But also, I mean, this is an open source project. It's evolving. The hope is they'll improve. Yes, another question.
So as you look through this for this talk, did you notice much difference between these kinds of estimates and the standard code profiling you might do for, right? If you're trying to just determine where your code is spending its time.
Mhm.
In other words, if I just make my code more efficient, it's not, yeah.
Yeah, if your CPU, if you're using your CPU less, then you will necessarily make your code more sustainable. That's just a fact. So yes, whatever you do to improve your code in terms of its runtime is going to improve the emissions. That's just because less is always better in this case.
But in addition to runtime, do you know if this does anything? I mean, and it's fine if you don't, but if you're looking into it, if you know that this treated, say, IO differently from CPU time, from GPU time,
Right, so
in terms
there's
of
that's
energy
where things
cost.
get a little bit more complicated, is that yes, different kinds of operations are have different costs. And I think that is included in this model. So if you need to trade off, I don't know, memory for disk operations, for example, that could have different implications. But again, I'm not 100% into like the details of that.
Thank you.
Okay, I'll go back to my slides. I'll just I noticed that my slides were in the wrong order. So I'll just point out one more kind of direction that we could all go to improve sustainability of research computing is to think about the conceptual frameworks that we are thinking of. This paper, Hype Sustainability and the Price of the Bigger is Better Paradigm in AI, is a really interesting paper that thinks a little bit about the cost of the bigger is better paradigm. They point out that the more specialized the compute is, the less energy it uses. So really big models that do things that are very, very general in nature may have much larger cost in terms of their usage versus the things that are more specific. And they also point out that the tasks that they've looked at, so they did a really interesting kind of comparison across multiple different things. The paper is a lot more than what I'm saying here, but one of the things they did is to look at different models for things like medical imaging, computer vision, natural language. And they just note that for a lot of them, things like model size, GPU memory used, and so on, does saturate. And so they just raise the question whether the direction that we're going in right now as a research community, especially around very large models, is all that productive, and whether the costs that this has is worth the effects that it's having. They suggest that right now we are all moving in this red arrow direction where we're getting increases in progress by using more and more resources more intensively. But there's an alternative direction of research we could take, which is to try to improve specific task performance while reducing computing resources. And that's a fruitful direction for us all to think about. So that's a lot more general than these specific tips, but I think is also worth mentioning. To summarize, to improve the sustainability of your compute, measure what you use, strategically shift your compute to energy efficient resources. The cloud is one approach to that, and think whether you could do better with less. And with that, I will thank my colleagues at the University of Washington eScience Institute who are involved in this CloudBank project that is sponsoring this Cloud Clinic and many other activities. And I'm happy to take any questions you have.